Now, when we talk about the structure of the Earth and its layers, we start off knowing that there's three basic layers to the Earth. We have the crust, which is the outermost edge. We have the mantle, which we're going to see in this portion here, and that's broken down into the upper and lower mantle. And then we have the core of the Earth, and that also is broken down into two layers. We have an inner core and an outer core. The crust is what we typically think of as the rock. Okay, it's the lithosphere, it's the sphere of rock. We have two different kinds. We have continental, which forms the land masses, and oceanic crust, which forms the bottom of the ocean. The very top of the mantle is also going to be a rock, and that forms the lithosphere, which we can see here as being a little bit of the crust and the upper mantle. Below that is the asthenosphere, and that's what the plates slide over. So it's a more liquidy layer of rock, and that's what the plates are moving on when we talk about plate tectonics. Now, below the mantle, we have the core, and we have two different cores there, one's solid, one's liquid. And the interaction between these two, the rotating of the core, is what generates our magnetic field. So we have a magnetic north and a magnetic south. We'll learn that that can flip every once in a while. And this is what our compasses are attracted to. We have this magnetic pole, and our compasses are going to point towards magnetic north. So it's not true north, which is geographic, but it's going to point towards magnetic north. And that's generally close enough for our navigation purposes. So the lessons will go through these layers in a little bit more detail. I just wanted to show you where they are and show you a quick picture of it. But also how we study them kind of is an interesting story in itself. We can look at the crust and we can study the crust fairly easily. We can go down to the bottom of the ocean and collect samples from the oceanic crust, continental crust you can go out in your backyard and find the samples of. So that layer we know fairly well. To get to the mantle is where we run into problems, because if you were to dig to the mantle, as soon as you broke through, you'd create a volcano, and that's generally not a great place to be studying. So most of our knowledge of the inner layers of the Earth comes from the study of P waves and S waves and how they move. So by studying this movement of the P and S waves as they traveled through the Earth, it gave us an idea of what was solid, what was liquid, how dense it was, and that's how we've painted the picture of what the inside of our planet is like. So our knowledge of the inside of our planet is based mainly on evidence that we assume coming from these wave patterns, but also by studying some of the products that have been brought up. That's how we know a little bit about the mantles, by looking at lava flows and things like that. But we can't actually get down into the mantle or into the core to study it. So most of our knowledge comes from indirect methods. Okay, so that's it for our video today. Good luck on your quiz and your lessons, and we'll see you in the next video. So to begin, let's talk about what is continental drift. Alfred Wegener was a scientist, a geologist, and he looked at a map and realized that South America and Africa, if you looked at their coastline, they kind of fit together. Now, this was kind of an interesting phenomenon for him to look at, because one of the things is it was a 90-degree angle on both of these, and that's not a very common shape in nature. And to find two of them that were separated by an ocean that looked like they at one point in time matched together, he hypothesized that several million years ago, all of the land masses might possibly have been joined together, and that over time these land masses were moving apart from each other. So if you look here in our picture of Pangea, and we'll talk about that quite a bit, you can see the same area here where Africa and South America were joined together. And over time, what's happened is they've migrated away from each other. And that's what the idea of continental drift was, is that these continents weren't solid. They weren't one single piece. And that went against what most people thought. Most people thought the crust had to be one solid piece. And if it was, there's no way it could move. And Wagner proposed that rather than it being one, it was a series of different ones, and these continents were able to move apart from each other. Now, once proposed, people started looking for evidence. And what we found were a whole bunch of different things. We found that there were mountain types. You can see the mountain types here were the same of where these places were thought to be once together. You could find fossils of animals that only seemed to link up together, and fossils of plants that did the same thing. And by playing around with the continents and putting these evidences together, what we were able to do is put them together. That's how we got the shape for Pangea down here. You can see all of this evidence, how it lines up, kind of shows us that at some point in time these had to have been together. And this was the evidence, and like I said, there's a bunch of it here that shows it, but Wagner did have problems trying to convince everybody that this is what really happened. So why wasn't Wagner's idea accepted right away? Well, there were a couple things. It was a change in the way we thought of the crust. We thought the crust had to be one solid piece, and now we were saying that it was different. There was belief that the Earth was static, that it was the way that it always will be, and it's the way that it always was. But this would mean that it was dynamic and that it was changing, and that was kind of a new thing for people to think of. But also, there's a significant lack of a mechanism. If we had these big pieces of the Earth here moving around, well, what caused them to move? What was that force that was doing that? It couldn't be something as simple as wind or waves or something. So we lacked this mechanism, and because of that, a lot of scientists rejected Wagner's hypothesis, even in lieu of the evidence that showed that it was probably correct. Okay, so that's it for our video. In the lesson, they'll go into this in a lot more detail. Good luck on your quiz, and we'll see you in the next video. Okay, so let's let our story begin here, where we're talking about deep ocean trenches. Prior to the 1940s, we believed that the oceans started off on one side and they kind of dipped down and formed the ocean bed here and kind of came up there, and we assumed that they were primarily flat at the bottom. Now, the way we used to measure depth is that you would have a boat sailing across, and as they got to a certain area, they would drop a rope, and they'd measure how much rope was out, and that's how they could tell how deep it was. And that worked really well and close to shore, but once you got out beyond where the rope could reach, they just called it deep. Okay, and this was primarily to make sure that boats didn't run into things as they were sailing across the sea, and you had to worry about more when you got in close to shore. Now, in the 1940s, there was a new invention out. It was called sonar. And what sonar did is if we had a boat, it allowed them to shoot down a sound wave, and that would hit the bottom, and then it would bounce back. And by calculating the amount of time it took and the rate of the speed of the wave in the water, they could then measure how deep it was. And when these boats with sonar that was primarily developed to hunt submarines were coming back from Europe at the end of the war, what they found is at the bottom of the ocean, there were mountain ranges and there were deep spots, and it just looked a lot different from what they had expected. So by finding this information, it kind of gave us an idea that the oceans weren't what we thought, and by looking at that information, we can start to see different ideas coming around. So here we're looking at our trenches, and our trenches are these deep blue lines here. And our deepest part of the oceans are going to be like the Marianas Trench, which we'll see over in here. Okay? And these trenches were where we had deep, deep water going on. Now, conversely to the trenches, we had our ridges. And most of the ridges, perhaps the most famous one, is this Mid-Atlantic Ridge. And we can see that one that goes right down the Atlantic Ocean here. It actually splits Iceland and then kind of goes down the middle of the Atlantic. And that was something new to us. We had no idea that that was there. And we can see some of these other ridges as well. And what this gave us is an idea of what was causing this, what was going on, what at the bottom of the ocean is happening that's allowing this process to occur. So here's our nice little picture. It kind of shows us what's going on. We have our continental crust here, and then we have ocean over here. And you can see that we have two primary areas I want you to look at. We're going to have a trench, and the trench, you can see it's right over here. And then we also have what we're calling this ridge, this mid-ocean ridge here, and a rift valley here. And what we noticed is that as these two plates, and we notice a split in the plate here, that's what a rift valley is, and you can see this split over here. As these are moving away from each other, it's creating a hole or a gap, and we have magma coming up through that gap, and it's forming new ocean rock. So this is the formation of new crust is going on right here, right in the middle of this rift valley here. Now, if that's going on, what it's doing is it's causing the surface of the Earth to get bigger. The crust of the Earth is getting bigger. So the Earth isn't expanding, it's about the same size. So that means somewhere we have to get rid of crust. And we notice that that was happening at the trenches, where this oceanic crust here is being subducted underneath the continental crust, and as it gets forced down, it would melt, and we'll see what happens on in different places. but now we're losing crust over here. So over here is where we're losing crust, and over here is where we're gaining. So the surface of the Earth is going to be about the same size. The crust of the Earth is going to be about the same. The Earth is not getting bigger, it's not getting smaller, but we can see where this process is happening. And by looking at these, then we looked for evidence to see, well, are the seafloors really spreading, or is this just kind of happening as it's going on? Okay, so once we discovered seafloor spreading was happening, then it was time to look for evidence so that we could prove that this was going on, that we knew this was the case. Now, one of the things that they found is we learned later on that you could just go down and look, and by sending down submersibles, we saw that there's evidence of volcanic material going on along these long mid-oceanic ridges, and that would show us that there's some kind of mountain building going on. It didn't show us that it was spreading, but it did show us that there was the activity going there that we would assume if there were spreading going on. We also developed ways to age rocks, and we found that the rocks located here, right by the Rift Valley, or where the mid-oceanic ridge was going, were much younger than the rocks we found further away. So by bringing up samples and testing those samples, we were able to see that these rocks here are younger, and then the rocks out here were going to be much older than the ones that were just being formed. Now, in this process, we discovered this paleomagnetism that you'll hear about. And what that tells us is we could look at the rocks, and some of our minerals, like hematite and magnetite, that are magnetic, lined up differently. And magnetite, which is actually magnetic, it would show us that the polarity of the Earth had switched over time. What that means is if we look at our Earth and we have our magnetic north and our magnetic south as it is now, that every couple of years, and not like a few years, but geologically a short period of time, like 10, 20,000 years, we would notice that the Earth's magnetic poles would switch. And our north would be where the South Pole was, and our south will be where the North Pole was. And we noticed that down here in our rocks that we had these bands of normal polarity, reverse polarity, normal polarity, reverse polarity. And by looking at that and seeing that that pattern was mirrored on both sides of this ridge, kind of gave us the hint that we had this seafloor spreading going on. Now, seafloor spreading kind of gave us an idea that Wagner's hypothesis of continental drift might have had a little bit more to it than we gave it initial credit. And when we take both of these together, we came up with a brand new theory, and we'll talk about that one in the next video. Good luck on your lessons and your quizzes this time, and we will see you in that next video. Okay, so let's talk about the theory of plate tectonics. The theory of plate tectonics is kind of unique because it's one of the few theories that we can actually see how it changed over time and developed. It's a young idea. One of the neat things is it took a bunch of different ideas and blended them together to make it into one unifying idea. And that's the unifying idea that we use for earth science. Now, plate tectonics took the idea of crustal plates from Alfred Wegener, and that continents move and these plates move, and looked at the evidence of seafloor spreading and came up with a mechanism for how all of this works. And that's what made this theory so believable and makes it so that currently that's how we think the Earth works. Now we can see that we have all these different plates, and you can see them on our map here. And notice that these plates are where there's trenches that we talked about, and also where we found these mid-Atlantic ridge and other ridges that we've talked about. So we found that there were borders to these plates, and in doing so, we could also see where they were moving. And we noticed that where we had the mid-oceanic ridge, and you can see it right here, that this plate was moving, or the plates were moving away from each other there. And that's what we would expect with seafloor spreading. We also noticed that we had plates that were moving into other plates, and that's where we had subduction and things of that going. So these ideas that we had from seafloor spreading led us to believe that we can look, and here's the actually spreading, and we can see where South America is moving away from Africa, and that kind of showed us what Wagner was trying to say. So the Earth's crust is broken into plates. These plates are actually moving, and we have evidence to show this. So because the Earth's crust is made up of all these different plates, these plates have to interact in areas. And we call this area of interaction a boundary. And there's only so many different kinds of boundaries we can have. And we're going to go through those real quickly. But before we do, I want to show them to you real fast. Now we can have two plates that are moving apart from each other, and this is what we call a divergent boundary, and we'll see that one in this slide. We can have plates that are coming together, so they're going into each other, and we call those convergent boundaries, and we'll cover those next. And then we can have plates that aren't moving towards or away from each other, they're kind of moving side to side. And those are what we call transform boundaries, and we'll talk about those last. So let's start with our divergent boundary. Divergent means that they're moving away from each other, and that's what the arrows are showing us, that we have this plate moving in this direction and this plate's moving in that direction. And as the plates move away from each other, they create this gap. And in this gap is where we see magma rise up and we form new mountains, new material, new crustal materials. Now, we can have rift valleys on land or in the ocean. In the ocean is where we have our mid-Atlantic ridges. There's a rift valley in East Africa, which is pretty popular. And that's where you can see the continent is actually being ripped apart because it's on two separate plates. So, divergent boundaries, we see the plates moving apart from each other, and we see the formation of new material. Okay, so let's talk about convergent boundaries. Now, convergent boundaries are where we have two plates and they're moving towards each other. They're crashing into each other. And these are going to be distinguished based upon the type of crustal plates that are interacting. So in this case, we have an oceanic crust, which you can see here, and then we have our continental crust, which is going to be over here. Now, the oceanic crust is going to be more dense. It's going to be a little bit denser than the continental crust. And because of that, where these two collide, this oceanic crust is being forced under the continental crust. And that's in an area we call a subduction zone. And where these crusts are being pushed under is where we see our trenches. We have these oceanic trenches. Now, as this oceanic crust is being forced down into the mantle, it'll melt away. And as it melts, we see new magma forming, and that new magma is going to rise up, and we get these continental volcanic arcs. So you can see that these volcanoes are going to form a ways away from where the plates are actually interacting. There's a distance here, and that's because that's where that plate's being forced under and melting. So an oceanic and a continental crustal convergent boundary, we generally will find a trench, which is a deep part in the ocean, and you can kind of see that here. And then a lot of times we'll find this continental volcanic arc. So those are the clues that we would look for that this is happening. Now, if we have oceanic and oceanic crust, it's an oceanic convergent boundary, we're still going to see the same types of things. We have oceanic crust over here, and we're going to have oceanic crust here, and we're going to have this subduction zone again, and one of the plates is going to slide under the other, and as that happens, we're going to see another trench. These trenches are where we get our really deep trenches. Now notice that this plate over here has some oceanic crust to it, and then ultimately it also forms some continental here. So we can have both on the same plate. They don't have to be one or the other. Now, once again, this oceanic crust is being subducted. It's going to melt, and we get this magma come up, and we're going to see this volcanic activity. But here, notice it's not on the continental crust. So what we end up with is a volcanic island arc. And things like the Philippines or Japan or Indonesia are going to be these volcanic island arcs that we can see around the world. The Aleutian Islands would be another good example of this. Now we can also have continental convergent boundaries. And what we see is we have continental crust here and continental crust here, and they're migrating together. And at one point there might have been some oceanic which got forced under, and we had a little volcanic activity. But this one I like to think of more of as a car wreck. And what happens is we have a really good example where we have the Asia plate up here, and then we have the India plate as well. And the India plate is traveling into and slammed into the Asia plate and caused this great collision, and that collision was the Himalayan mountains. And that's where we find Mount Everest. So while these two plates are hitting, instead of one subducting under the other, they just kind of buckle and are upward thrust a little bit. And that's how we get these really high mountain ranges like the Himalayas. Now in this picture, we have our transform fault. And that one's going to be a little bit different. In the previous examples at divergent, we had new material being made. At the convergent, we're kind of losing crustal material. And at the transform boundaries, we're not having any at all. There's just the same things. These plates, as you can see, are just going to be moving past each other. So there's no subduction here. It's just going to create a fault, and we'll talk about that a little bit more. But what these plates are doing is they're kind of sliding past each other, and that's what we call a transform fault boundary. So Wagner's big flaw was he didn't have a mechanism for how these big pieces of the earth could move around. And what we found is that the core has some uneven heating, and that's going to cause a mantle to have some uneven heating, and we get these plumes of heat. And you can see one of them over here, and you can see one that's all the way up here. And as that plume of heat comes up, it's going to hit and create these currents. So as I'm moving upwards, I'm going to create this current. You can see that we have mantle material moving this way. It's going to hit the crust, then it's going to spin. It's going to cool off, come back down, heat up again, and it's going to go around. And we get these huge currents, these convection currents going in the mantle. Now, as this convection current here, we'll just blow this part up right over here, we have this convection current of mantle coming across this way, and it's going to be moving in this direction. The crustal plate that we see above it isn't going to be smooth on the bottom. It's going to be kind of jagged and uneven and all like this. And as it's sitting there with this current moving, it's going to push this crust in this direction. So what we notice is that's what's going to drive these plates moving. When these plumes come up, we're going to have areas where that plume's going to arise, and it's going to come up and split and go this way, and we have two separate things, and that's where we're going to have our divergent boundaries, where these two are going to be forced away from each other. And if they're forced away here, then this one here is going to bump into another one, and we could have our convergent boundary right over here. And if there's another plate that's lying next to it, that's where we can get our transform. So these mantle convection currents is what's pushing these plates around, and that's why we have plate tectonics. Okay, so that's it for the video. As always, this was just a real quick overview of it. You'll get a lot more from going through the lesson. Good luck on the quiz, and we'll see you in the next video.